This is an AQA A-level chemistry question, predominantly based around the kinetics and equilibrium topics, with a little bit of organic thrown in. So try each section, pausing as you go, and then review your answers. Here's parts A and B, part C, part D, and finally part E. Total of 12 marks available. So let's go back to parts A and B. A student carried out an experiment to determine the value of the equilibrium constant Kc for the esterification reaction between ethanoic acid and ethanol. And we've got the word equation provided. You are then needing to write a symbol equation for it. So you've got to be familiar with the functional groups. You've got to be able to recall the key principles of nomenclature. And we get this, remembering that it is a reversible reaction. So the CH3COOH, my C2H5OH, written slightly differently there, ethanol, my ethyl ethanoate, CH3COOCH2CH3, and my water on the end, because that will be produced because it's a condensation reaction. The skeletal formula can prove difficult for people. Simply remember that the end of a line is a methyl group unless otherwise shown. So we're looking for this. You don't have to have the line going up and then down. It could be down and then up. It could be up and then across. You simply have to have the right structure. The spatial arrangement could differ. Okay, we'll move on to part C. Student used a small amount of conch sulfuric acid as a catalyst to increase the rate of reaction. State in general terms how a catalyst works. This is such an important question because you can be asked about catalysts in two ways. You can be asked for a definition or you can be asked how they work. We want, for how it works, that it provides an alternative reaction pathway and that lowers the activation energy. If asked for the definition, it would be speeds up the rate of the reaction, but does not get used up in the reaction. You've got to get those pairs the right way around. Moving on to part D, we've got quite a lot of information here. We've got a student mixing molar amounts of ethanol and ethanoic acid. So we've got initial moles, we've got acid being added to the mixture, we've got it being left for a week, we've got a Kc value, and we've got the volume of sodium hydroxide that we're actually calculating. There's a lot to think about here. This is a challenging question. So let's see how we can build those marks up. In the first instance, it's a Kc calculation, so write out the expression for Kc and do that with care. You can see we've got our products, our ethyl ethanoate and our water on top, and we've got our reactants on the bottom. Now from there, we can start thinking about figures. We don't have figures necessarily because we know how much we started with, but we don't know how much of the reactants we ended up with. So we're going to now incorporate the value of X. X is the equilibrium moles of ethyl ethanoate, and it's also the equilibrium moles of water. And we know they will be the same because it's a 1-to-1 ratio in the equation. So for every 1 mole of ester that's made, there will be 1 mole of water. Similarly, the molar ratios can be carried forward that if I've made X moles of ethyl ethanoate, then I've used X moles of ethanol and ethanoic acid. So they become 0.035 take X in both circumstances. 0.0435 of ethanol, take away X. 0.035 of ethanoic acid, take away X. You can see it's one of the more complex questions within this topic. Where do we go next? Well, if I then rearrange this, I can say that Kc is equal to x squared over 0.0435 take away x squared. I also know what the Kc value is, so I can now square root all aspects of it. And I can see that my root of 4.07 equals x over 0.0435 take away x. We can do some rearranging there. And when we rearrange, we can see that X comes out as 0.0291 moles. Now that also means that I can work out my equilibrium moles of acid. I started with 0.0435. All of this has been building up to you being able to work out that 0.0435, take away that 0.0291, gives you 0.0144 moles of acid. Why is that important? Well, because the final part of this is a titration calculation, essentially. I am neutralizing the remaining acid, or more specifically, acids, because we are still not quite there. We also added a tiny amount of sulfuric acid catalyst. The total moles is therefore the 0.144 plus the moles of acid. But by acid here, we're meaning H plus ions. That's what we want. And we've now got to consider that the sulfuric acid is diprotic. So my 0.0144 moles of ethanoic acid, I've now also added 10 by 10 to the minus 4 moles of H plus in my sulfuric acid. I now know that I had 0.0154 moles of H plus. I'm reacting that against NaOH. I know that it's a 1-to-1 ratio because I know my number of H plus ions and my NaOH, each sodium hydroxide will yield 1 OH minus. It's monobasic. So if I know my number of moles of sodium hydroxide, 0.0154, and I know my concentration, 0.4, which is all the way up here, I can work out my volume, which I'm going to have to remember is in decimeters cubed, so I multiply it by 1,000, giving me a final answer of 38.5. There's a lot of work to do there, but there are aspects of that that are easy marks to pick up. Writing out the expression for case C, working out volume if you can get to a point you have a number of moles in concentration. So do always try to get as far as you can, even if the question itself looks a little overwhelming. Finally, moving on to part E, how could the student check the mixture had reached equilibrium after 1 week? So we're moving into practical territory here. We're thinking about practical questions, required practicals. What we're looking for here is that you could test a range of samples, and within that range, at least one of them should be tested after it has been at equilibrium for a week. And what we should see is that the results haven't changed after a week. That tells us equilibrium has been reached. It's still not, or it's not still changing. That takes us to the end of this question. Thank you for listening.